pop-up seminar series. So my name is Asim Rastogi. I'm a researcher at the Microsoft Research Lab in India. Like all of us here, I contribute to and use STAR. So let me say a few words about what this seminar could be, what is our thinking behind this seminar, and setting the agenda of the meeting today. So we are starting this seminar with co-organizing with Nick, Lucas, Theo, and Joshua, who are all on the call. Our thinking here is for it to be a forum where the STAR community can interact with each other and exchange notes. And this exchanging note can take various forms. It could be learning about each other's libraries. It could be sharing experiences of using STAR, what works, what doesn't work. It could be even about what future directions should STAR go to, what should happen next in STAR as such. So we are thinking of this seminar as a very informal event, and what shape it takes is actually up to us. We should collectively decide what do we want out of this seminar and what format should it have. Aymeric kindly has volunteered to lead a discussion on what this seminar should look like and what each of us wants from this seminar towards the end of today's session. So thanks to Aymeric. So if you have some thoughts on what it should be and what would you like to get out of it, then please do chime in that part of the session today. But as far as like informally, like anything that's related to STAR is of interest to all of us. So we are looking for proposals. If you think you would like to present something that's related to STAR, I think please do send us an email. Please do get in touch. We would love to hear from you. We are actively looking for proposals there. Also, I think if you want, we can all introduce each other in the chat so that we know who all are joining and we know our STAR community better. So today's session is we have two blockbuster talks, one by Vimala and Lucas. So I'm thinking we'll have say 15-20 minutes per talk, including question and answers. And then towards the end, Aymeric is going to lead this discussion on what this seminar could be and what all of us want out of this seminar. So so that's it. If somebody has a quick thought, please do chime in now. Otherwise, we'll just go into first talk. Okay, so I think let's go to the first talk. So first talk is by Vimala. Vimala is she's a third-year PhD student at IIT Chennai. She's working with Karthik and Casey. Currently, she's interning with us at Microsoft Research in Bangalore, working on slightly different things. I know that she's staying up late in the lab to do this, so much appreciated. Thanks for doing it. And she's going to tell us about a library for certified replicated data types in STAR. That's their paper that recently appeared in PLDI 22. So Vimala, take away.
Yeah. Hello, everyone. So first, let me share my screen. Is my screen visible?
Yeah.
Yeah. Hello, everyone. I am Vimala, a third-year PhD student at IIT Madras. I'm guided by K.C. Sivaramakrishnan and Karthik Nagar. So today I'm going to present our work on building certified mergeable replicated data types using FSTAR. And this work appeared in PLDI 2022. So first, let me start with a brief introduction about mergeable replicated data types and the problem that we are trying to solve, and then move on to FSTAR. So this mergeable replicated data types are data structures that borrow the idea of distributed version control systems like Git. And they apply this concept to arbitrary data types, not just text files. So as most of you will be familiar with the Git workflow, multiple developers can work on the same project by forking off several branches. And suppose when a branch wants to get update from another branch, Git performs something called as a three-way merge. So what it does is it gets the current state of the two branches to be merged and the lowest common ancestor between them, and then it performs successful merge. So MRDTs are also similar to that. So any sequential data type applied with the three-way merge function forms a replicated data type. So here's an example of an increment-only counter mergeable replicated data type. So let us consider that the state of the increment only counter is a natural number, and it starts with the initial state, say 7. And suppose two branches A and B forks off from this main branch, and they apply operations +1 and +14 on either sides, and the states become 8 and 21 respectively. Now, suppose when branch B wants to merge with branch A or A with B, it performs something, it performs a three-way merge. So it takes the current state of the two branches and the lowest common ancestor between them, and it performs the merge. So on the right-hand side is the three-way merge for the increment only counter. And from the diagram, you can see that the states converge. So on either sides, the state is the same. And we know that, so from this, we know that our three-way merge function is convergent, and it also preserves the intent of the data type. So in the increment only counter, what is the intent? So the concrete state at a branch must capture all the add events that are applied so far in that particular branch. So how do we concretize the intent? So we need a formal specification language to capture the intent of the MRDT. And we must also be able to say that our MRDT implementations are convergent. So these are the two problems that we are trying to solve in this work. That is, for any MRDT implementation, we must be able to say that it is functionally correct and it is also convergent. And we observe that even simple data types becomes more complex when they are made distributed. So we thought that we need machine checked proofs to say that a particular implementation satisfies the specification. So we have developed the Peepul and FSTAR library for building and verifying mergeable replicated data types. So here's the list of the MRDTs that we verified in this work. And using this FSTAR library, we are able to compose MRDTs. So what I mean by this is that we are able to build the composite MRDTs by combining multiple simpler MRDTs. And we are also able to reuse the proofs of the simple MRDTs in the proofs of the compound MRDTs. And the extracted code, so we extract the OCaml code out from FSTAR. And this extracted code is compatible with Ermin, a Git-like distributed database. So before getting into FSTAR, let me tell you the verification methodology that we use. So as I told that we need a specification language to capture the intent of the MRDT. Here our specification language is event-based. So we need a structure to capture this. For this, we use something called as an abstract state. So this abstract state is a set of events along with the visibility relation among them. And we have a concrete state which is specific to each MRDT. And we use a simulation relation to connect this abstract and the concrete state. So given a simulation relation for a particular MRDT, our proof involves showing that this simulation relation holds on every transition at every execution of the replicated store. And we also need to show that this simulation relation is strong enough to imply the specification, and it must also imply convergence. So now let me go to the FSTAR library that we have developed. So, so is my screen visible? Just to check. Hello?
Yes. Yeah, it is.
Yeah, okay. Yeah, okay. So this is the library that we have developed. This is the Peepul library. So as I said that we have a abstract state. So, so this is the abstract state of the library. So it consists of a set of events along with the visibility relation among them. So in our proofs, we mostly rely on the refinement types. So even in the abstract state, we have added a refinement on the set of events. So, so the refinements could be something like, so we say that all the events have unique timestamps, and we expect the visibility relation to be transitive, asymmetric, and irreflexive. And this property tells that suppose if event E is visible to event E prime, then we say that the timestamps of the events are like satisfy this property. And this property says that if like no two events can have the same timestamps. And the last one tells that all the events should have timestamps greater than 0. And then, so we have, so in order to provide a modular way to implement and verify MRDTs, we have used the FSTAR support for type classes. So here's, so we have defined a type class called MRDT. So it takes as input the concrete state of the MRDT, the operation supported by the MRDT, and the return value of those operations. And we expect the client of the library to have implementation of the following methods. So let me go over each of these things in detail. So for each MRDT, we must specify the initial state of the MRDT. And we also need to specify the specification of the MRDT. So what is the specification function? So given an operation and an abstract state, this specification function will return, give the return value of the operation based on prior operations applied to that object. And this is the simulation relation that I was talking about. So this simulation relation connects the abstract state and the concrete state. And then for each MRDT, we have the concrete do function and the concrete three-way merge. So what this concrete do function does is it takes the current state of the object and it applies an operation on that current state, and it returns a pair of updated object state and the return value of the operation. And this is the three-way merge function, which takes the LCA current state of branch A and B, and it performs the three-way merge. So having defined all this, we expect the client of the library to provide proofs of these four properties. So what this first property tells is that, so let me show you with the help of a diagram. So suppose there exists a simulation relation between an abstract state I and a concrete state sigma. We must tell that, so suppose if we apply an operation on the abstract state and we get I prime, and we apply the same operation on the concrete state and we get the updated concrete state sigma prime, we must tell that the updated states must be related by the simulation relation. So that is what the first property tells. And the second one is for the merge. So given that there exists a simulation relation between the abstract and the concrete states of LCA and branch A and branch B, we must prove that the simulation relation continues to hold even after the three-way merge. And the next property tells that, so the return value of any operation applied on the concrete state must match the value of the operation obtained by the specification function on the abstract state. And then the last is the convergence theorem. So here we say that if two concrete states observe the same abstract state, then those two concrete states must be the same. So this library is defined once and for all, and each client, each MRDT will be an instance of this type class. So let me show you one instance of this type class. That is the increment only counter. So as I told, we need implementation of the methods that is shown in the MRDT type class. So for the increment only counter, the state is a natural number and it supports two operations, add and read. And so it has this return value. So an operation can either return a value of type S, or it can return a bot. And the initial state of the increment only counter is 0. And this is the concrete do function. So if an add operation is applied on the concrete state, it just increments the state by 1 and it does not return anything. And the read operation, it retains the state, but it returns the current state of the concrete state. And so this is the specification of the MRDT. So the specification function, what it does is, given an operation, it tells the return value of the operation based on the prior operations. So for our increment only counter, the read operation should return the count of all the increment operations that are observed by a branch so far. So this sum function just calculates the number of, counts the number of add events in the abstract state. And the simulation relation is also the same. So this relates the abstract and the concrete state. So the concrete state will be the number of events in the number of increment events in the abstract state. And this is our three-way merge function, which is A plus B minus L. So having defined all this, we need the proof of the following four lemmas. So the first one is for the do operation. So this lemma goes through without any additional effort, and it is automatically proved by F star. And coming to the proof of three-way merge. So before that, if you see the three-way merge here, the states of LCA, A, B are all natural numbers, and the output of the three-way merge must also be a natural number. And you can see that this three-way merge has a minus operator here. So this does not type check until we give F star the information that A is greater than or equal to L and B is greater than or equal to L. So with this precondition, this merge function type checks. And so we apply this preconditions, and we expected the F star to make this property go through without any additional effort. But then we realized that we need to help F star in inferring the information that A is greater than or equal to L and B is greater than or equal to L. So we came up with this lemma called sum union. So what this sum union tells us that, so given the list of events in the LCA and the list of events in the delta branch A and that of LCA, the number of add events in the union of LCA and A is equal to the number of add events in LCA plus the number of add events observed by branch A. And so we prove this inductively. And so we have this precondition here that there exists a simulation relation between union LTR, ATR, and the concrete state A. So from this we can get the information that the condition that the concrete state A is greater than or equal to the concrete state of L, and similarly for B. So the next lemma is for the abstract merge. So having proved this lemma, the F star is now able to prove this particular property. And then the proof of specification and the convergence proofs goes through without any additional effort. And now this is the instance of the increment only counter instance for the type class MRDT. So we have implementations of all these methods. So we know that our increment only counter is verified. So we have so the code that I showed you, it does not execute the merge function. So what we did is we extracted the F star code to OCaml. So in F star there is a command line argument called code gen, which extracts the F star code to OCaml. So for our increment only counter, the code, the extracted code looks like this. Extracted OCaml code looks like this. So we have extracted the do function and the three-way merge. And we have used this three-way merge in the three-way merge of the Ermin. And you know, in the Ermin is also similar to Git. So you can create a store, do all the operations that are supported by the data type. And similarly, we have called the three-way merge in the Ermin. So what I'm telling is that the extracted code is compatible with Ermin. And coming to the verification effort. So in this work, we have used only the pure fragment of F star. We have used only total and pure functions. And we have used both intrinsic and extrinsic styles of proofs. And this table gives the verification effort for this work. So this is the list of MRDTs that we verified. And the second column gives the number of lines of F star code for the particular data type implementation. So this number is the number of lines of OCaml code that if we had to implement it OCaml without any proofs. So this is the count of those lines. And this is the lines of proofs we took for verifying each MRDT. And the next column shows the number of intermediate lemmas that we used in our proofs. So from this column, we can see that for like F star is like able to prove many of the lemmas, many of the MRDTs without any lemmas or just a few. But the developer can make a choice by adding more lemmas and helping F star arrive at the proof faster. So we have shown this for 3 of the examples. Like as you can see, when you increase the number of intermediate lemmas, the verification time considerably decreases. So it is the developer's choice, whether you want to go with more verification time, or if you want less manual effort. So it's developer's choice to add more lemmas, or you can leave it to F star to prove the things. So that's it from my side. So
yeah,
happy
thanks.
to take questions.
Thanks, Vimala.
Yeah.
Are there any questions? Please just unmute yourself and speak up. I think everybody should have permission to unmute.
This is really cool. Oh, sorry. You go ahead.
Oh, go ahead. Oh, okay. So I have a specific question. I saw that your merge function has a precondition.
Yeah.
And
yes.
So when do you call this merge function? I mean, at extraction, you lose the precondition, right?
Yeah. Yes.
So is this merge function used in secure programs, or anyone can call it?
Secure programs in the sense?
So if you don't have the precondition of the merge function, then anyone can call with wrong input that function, right?
Yeah. So see, this three-way merge is already verified. So this we have simulated the replicated store using this abstract states, and we have preconditions that should hold. So this three-way merge is obtained after having all these preconditions. And when you use it in any, implementations, you are guaranteed that it will converge and it will not, it preserves the intent of the data type. That is the guarantee that you get. This precondition, we just supply it for this merge to just type check.
Okay.
Well, maybe I can raise Cesar's worry. Like, if any of your functions have preconditions star and you extract them to OCaml code doesn't really have to satisfy the preconditions.
Okay. OCaml function doesn't need to satisfy the precondition. Suppose if you take the case of the ermin, if we were to use the same increment only counter in the ermin, so the increment operations, it only increases the current state of the thing. So anyway, your state of the branch A is going to be greater than that of the state of the LCA, right?
So I think we can take it offline. Nick has his hands up.
I thought Josh, was it Josh who maybe also had a question before me? Go ahead, Josh.
Yeah, I mean, my question is relatively simple. I just was looking at your numbers for the proof effort, and it looks very encouraging, except for the very bottom one, which seems more difficult. So I was just curious about the commonalities between the top proofs being easy and how the bottom proof is difficult.
Okay. So the proof time, so the top proofs take lesser time because the implementation is more related to the specification. So when as the implementation gets when the implementation is far removed from the specification, your verification time it increases. So your simulation relation will become big as your MRDTs become complex. And we need to supply more lemmas, and the verification time also increases. So it depends on your implementation and the simulation relation that you write.
I see. So the queue has a much more complicated implementation than the other. I see.
Yes, the specification and the difference between the specification and the implementation. Yeah, that makes the difference.
Okay, so maybe the last question, comment from Nick.
That was really cool, Vimala. Thank you for sharing. My question is kind of a non-technical one, maybe a more social question. I'm wondering how you and your team managed to, get up to speed on F-star using things like type classes and so on, which until recently weren't very well documented. I'm just wondering, like, how did you all acquire this expertise, and what can we do to help others acquire similar expertise?
When this project started, to be frank with your question, this F-star was offered as one of the courses during my first year by Casey. So that's how I got to know about F-star. And then why we used F-star for our work is that ideally we want an OCaml out of the work. I mean, OCaml out of verified OCaml implementation, and F-star, F-star compiles it to OCaml. So that's right. So initially, most of the things were like trial and error method only. Like none of us were experts, and as we started doing the proofs slowly, like we started from the simpler MRDTs and we went to more complex ones, and by trial and error method we acquired some knowledge. And I remember for type classes there was one small document but not a very detailed one, so that also we explored by by performing experiments. Yeah.
Thank you. One thing I could say is that, on some of these things like that seem to take a long time, like the queue example and so on, and Alex remarked about the R limit 1000 and so on. Like, if you, I would be happy to take a look and maybe help you guys profile it and see if we can make these proofs go a little faster and be more maintainable. Maybe we can follow up separately about that at some point.
Yeah, sure. That would be really useful. Thank you for that.
Okay. Thanks, Vimala. Thanks for the talk, and thanks again for staying up late in the lab to do this. So we should move to the second talk. Our second speaker for today is Lucas. He's a postdoc at INRIA in the Prosecco team, and he one of the few people who do very cool stuff with tactics, and that's what he's going to, I guess, tell us about usability and how to improve the tactics in F-star. So Lucas, take it away.
Thanks, Asim. So hi, everyone. I will share my screen. Can you see my screen or? Yeah. Okay, cool. Okay, so today I will speak quickly about something I've been working, some tooling. So it's about an interactive REPL for tactic in F-star. So first, let's motivate why and what would be an interactive REPL for tactics. So the first thing is that, so in F-star, the cool thing is how nicely and easily we can define refinement types, right? We can have dependent and refinement type with automation. And so we can define really cool things. So here, a very classical natural number and positive number example, but we can, for example, say what is a composite number. So here, X is a composite number if there exists some N and M such that N times M can be equal to X. And then we can already have some nice type like composite or prime numbers. And the fantastic thing is that F-star will be able to prove, for example, this list of prime number is indeed a list of prime number. So that's great. That's a great UX because in comparison to other proof assistant or dependently typed language, where you have to sometimes write manually proofs for very trivial stuff like this, here in F-star, we are quite happy because everything is a bit magic. So the magic is nice, but sometimes the magic also vanishes a bit. So for instance, here, if I want to try to type check that 6 is a composite number, here, because of my encoding basically of composite. Oh yeah, thanks Alex for the, yeah, it's a, indeed. Yeah, bad specification. So yeah, here, for instance, 6 is clearly a composite number, but we cannot prove it automatically. Why? Because of the exist quantifier here. And the solution here is to explain with some patience to the SMT solver that we can show that 2 times 3 is equal to 6, and then that this exists actually out. So here, that's working. We could do this in a number of ways. So for instance, we could construct manually the term of proof, and so with this syntax here, by explicitly instantiating things, witnesses. But it's also a bit painful. We could also use tactics. So that's the goal of this of what I'm presenting today. So here I'm for instance unfolding is composite, so the function I declared above, and then I just give some witnesses explicitly, and so I can solve the goal. So here I'm using tactics, and tactics are just meta programs that build terms and interactively build terms against a proof state. And usually in languages where when we can use tactics, there is an interactivity. That is, we can play with the goal of proof and see some feedback. So for instance, in FSR, I could write here dump and get the goal, the current goal. So if I move my dump here, for instance, I see that I indeed unfolded the thing and pushed a witness. So in FSTAR, we would do this by moving basically this dump and rerunning the tactic again and again to see how it evolves. So tactics are super useful in FSTAR when basically the SMT is lost. So when it's too slow or it's completely lost because the context is too big or we are dealing with too complicated things. And sometimes also you need some fancy normalization on some subterms or stuff like that. Or you need to deal with, I don't know, like terms with nasty terms with lambdas inside and stuff like that. So you need some precise control. And the thing is, in our Emacs mode, we have this nice possibility of checking things one at a time for top levels. And we would like to have the same thing for tactics, since we could be able to directly see how the goal is evolving. So here, a small example, which is purposely simple. So I define a small function here, double, that just doubles a number. And then I have through a sort of lemma where I want to prove that double of 10 is 20, which is quite easy, and some stuff about this +2 function on which I have some lemma. So if I ask the SMT solver right now, it won't be able to solve it because of some encoding again. And I could write some tactic. So here I could write split to split the goal in two and see like the result. So I see here the thing, but again, I have to insert thing manually and it's becoming a bit painful at some time. So now in my Emacs, I can directly run here, so run a small interact here command that will basically open up a small window where I can type commands directly. So for instance, if I write dump of something, it's processed as one tactic. I can directly write, like in Coq, my split, for instance. I split my goal in two, and I can keep going and play with my goals. So just to make a small demo here, I would, for example, normalize this double thing, this double function here. So I can just do a delta reduction on the goal and get this addition. I can then just normalize the primitive operations, so the plus, get my result, and keep going with TREPL to say that 20 is the same as 20, so my goal is solved. So I make a little mistake here. Yeah, and so then I can just see that here I need to fill a witness, so I can give a witness, and I'm not really sure about which witness I should give. So let's say it's 10. Right, 10. Then I normalize things up again. I can use, for example, computer, and I see that I was wrong. So it was not 10 the witness. So that's really a shame. But the nice thing is that actually I can just put my cursor anywhere and come back, and it will revert to the goal from before. So I can just go back to my witness, put 2 because that's the actual correct answer. And then here, as you can see, my goal is almost solved. I can also, just for the demo, I can also have let bindings, for instance. I can have this, for instance. And now I can apply this H, well, the +2 function lemma argument, my hypothesis. So I can just apply some of this. And here I'm almost done, so I can, again, just go ahead and compute things and use, again, my nice TREPL. And here the proof is done, and I end up with a normal Emacs buffer. So I can just come back and redo my proof. It works nicely. So that's the first thing. But also, the thing is, we can also want, we might also want some more interactive things or some more graphic thing. For example, if you wanted to like pretty print matrices, you would like to see them in like a nice format or some geometry or whatever you can. A smaller REPL in HTML to get more interactive things. So if I write here interact HTTP instead, so this is a tactic as well. This tactic will do something a bit strange, will pop some tabs in my browser. It's a bit slow because of the video, I think. It's really slow. Yeah, and so we get also the same kind of REPL thing. And here you can see that the thing is aware of subterms. So actually you can even play with the mouse with subterms. Like you could say, oh, this I would like to normalize this subterm. So you can click and just go ahead and normalize by the mouse or stuff like that. So I won't do the demo again because it's the same term, right? So I will type the same tactic. But yeah, so that's basically it. That's what I wanted to show, I think. I'm not missing something. I think it's, yeah, I think so, I'm done. I don't know if you have any question.
Wow.
Plenty of questions.
So, oh, I think I cannot hear you assume, because I see you talking, but.
No, sorry, go ahead. I'll ask later. So I had a question. If
I mean, I'm at loss as to where to start, even because this is entirely new ground to me, and I've never used tactics in FSR, mostly because there is no documentation on them, and things like delta make absolutely no sense to me because this is not a name that could make any sense to anyone outside the topic from the beginning. And what I'm currently seeing is a step-by-step proving, which is entirely out of my reach. Well, I guess unless I start actually working with tactics, because I don't see any analog for such a mode. in regular proofs that go by invoking lemmas. I mean, is there even an upgraded Emacs F-star mode that allows step-by-step into lemmas, or what? How do I even repeat this?
Okay, so you mean, so this thing is, so usually in the Emacs mode, you don't have this stepper for tactics. So yeah, it's a new thing. But then, I don't know, like, so what you were saying is like, you don't see what's the point of using tactics for your proofs, you mean, or
No,
maybe?
the point is crystal clear.
Okay.
The how is not.
Okay, yeah, then we need some more documentation.
You presented some sequence, a sequence of intrinsic or internal tactic invocations that eventually led you to your goal being proved. But the names you used, I mean, I can deduce something from L to R, or, excuse me? Okay,
basically.
It's just that when I see a flow of invocations which as names do not make much sense to an outsider like me, with little to no prior experience with automated proofs, I cannot.
Specific. I think we should.
I can make sense. I can make sense of what are you doing and how you prove your stuff, but I cannot repeat it unless I understand the building blocks. And there seems to be a lot of building blocks, and there seems to be very little written text on how to operate.
Yeah, Alex, we should document it better. I think saying it for some time.
I'm looking forward to it, honestly, because I can see a lot of applications to my algebra stuff, because there are plenty of proofs I have done by hand. And sometimes proving stuff in abstract algebraic structures where your equivalence relation is not F-star's built-in equivalence sign, but a custom relation that just happens to obey the required rules of symmetricity, transitivity, and reflexivity, and proving stuff about objects in generic algebraic structures can sometimes be very lengthy. And I already wrote about that. Proving certain stuff about matrices sometimes took hundreds of lines of code. And when I see those lines from far enough, I can already tell that tactics can reduce that to maybe dozens of lines. But I cannot yet use tactics until I get knowledge about the building blocks.
Yeah. There is some documentation to be,
And, my first question was, how do I get this step-by-step interface? Because it will help a lot. Is there even such interface without tactics? Huh?
Yes, I think we'll have it soon.
I was just reading the chat. Because the chat is eluding my attention. It is down below on the screen, and I'm not always immediately realizing there is something new there.
No, I think the bottom line is that we all.
I see Nick is sometimes typing something, but I'm sometimes late to read it.
Yeah, I think we should move on. So Guido, you had a question, right? So we will talk to Alex hopefully soon.
I have already asked in the Slack chat about some kind of introduction and specifically introduction to writing and composing own tactics, because I can already see that the built-in tactics are not designed to work with custom equivalence relations. Like, they are all aimed at proving stuff about formulas involving the built-in equivalence. Am I right in that regard?
I think we should discuss more in depth later.
Yeah, it's too specific.
Okay, then you just stop me and
thanks, but again, thanks for pushing us, nudging us towards documenting it. I think it's hopefully we'll get there soon. Guido, you want to go?
Yeah, so Luca, it's a great talk. Thank you for the presentation. I'm wondering on how this stuff is actually implemented. Like, are there patches inside the compiler? Is it just external to it? Is this step-by-step procedure like trusted, or does it have to be like this kind of stuff?
Yeah, so the funny thing a bit is that I just added one thing to the compiler, which is built-in to just parse a term. So just a term to string, basically. And otherwise, it's just really just tooling. And so it's basically just, I expose also a socket interface, but just with camel extraction, so without any change to the compiler itself. So basically just socket plus something that takes a string and builds you a term, allows you to do basically everything. So yeah, it's pretty simple in terms of, it's almost all userland. So that adds no trusted part or things like that.
I see. That's great. That's great. So I mean, even if you do the proof step by step, then at the end you still have the fully spelled out proof that will just be type checked as usual, right?
Yeah, exactly. It's nothing to the type checker,
okay.
No change to the type checker or anything. Yeah.
Okay, that's great. That's great. Thanks.
Joshua, you had a question?
Yeah, I have a quick question if we have some time. The question is essentially that my understanding is tactics are extremely effectful. Like, they can do arbitrary effects, like, I guess, open HTTP, which I did not understand. So my question is about like rewinding. So like in proof assistant like Calc, you can like rewind the proof, and it seems like you can do so here, but it seems like, does FStar support like saving proof states so you can do arbitrary rewinding like this?
Yeah, actually, the tactic effect has exceptions. And so FStar basically builds a stack of proof states. And if you throw an exception, then you just when you catch it, then the proof state is so it's pretty simple actually. So it's yeah.
Okay, thank you.
Okay, so I think thanks again, Lucas. I think this was great. I just have one last question. Like, when is it getting into master?
Yeah, that's a great question. I think I just need to merge that pair of term to string thing, but it's like quite small. Okay. And otherwise, I just need to polish things. But yeah, soon I hope.
Looks great. Thanks. So I think thanks to both the speakers. I think I really enjoyed the sessions. I hope everyone did. So for the last part, I think we have 10-15 minutes. So Aymeric, do you want to lead the discussion on like what form or shape should the seminar take going forward?
Yeah, sure. Just before that, I just saw that there was one last question from Santiago in the chat for Luca. And Santiago was asking, how would you get a replayable proof after completing a proof interactively through HTTP? So Luca, if you have an answer.
Sorry, I hadn't okay, so basically the thing is I just exposed like a small API, so a small HTTP server, and so I basically just send some commands, some tactics to be run. So I can just actually my repo save a list of all the tactics that have been executed, so I can just replay that or craft the term that correspond to all of those tactics. So it's pretty so we can do so. We can replay the thing after. I don't know if it's answering your question or.
Gonna take that as a yes, I guess, in the meantime. Thanks, Luca, and thanks, I guess, to both the speakers for presenting today. Thank you, everybody, for coming. So I guess the last part is about having a chat and a brainstorming session about what you thought about this first seminar, whether it was up to your expectations, whether it was answering the questions you always ask yourselves about FSTAR, and more importantly, about how we can make the seminar evolve to make it so that it's basically something that allows us as an FSTAR community to grow together and to have everybody that gets a chance to ask the questions that they have. So I guess if any of you has remarks regarding the formats, for instance, did you think that 2 presentations in one session were too much? Did you think that you had enough time for questions? Do you think, for instance, that following this seminar and the talks that you saw today, you will be interacting with the speakers and talking offline about what they presented? So I guess this is, kind of free form. Please don't hesitate to chime in, either in the chat or by raising hand, I guess, and unmuting yourself. Okay, so I guess the first remark is from Catalin, saying that some way to catch up with the speakers afterwards would be good. I'm not sure, Catalin, if you have anything specific in mind. I guess at the very least, most of the speakers should be...
If the speakers hang around, maybe breakout session, the breakout feature of Zoom, but I guess also they could share emails or something so that people can catch up with them afterwards. I guess in this case, the first speaker was very late, so I don't think I would want to keep her too long, right? So maybe sharing email addresses would be enough.
So I guess on top of email addresses, would something like a small temporary channel on Slack related to each talk be useful? Yeah, okay. I guess George had the same idea. So I guess that's something that is easily doable. Just each speaker can create and advertise their own small channel on Slack, which can be archived a bit later. So that you can have follow-up discussions in a more structured way. Okay. Is there any other comment, remark, suggestions for improvements? Okay, top 10 cheat tactics sounds good. I guess that comes down to what Nick and Asim were mentioning about documentation on tactics being high on the list for the next few weeks / month. Yeah. So I guess if there are no particular invitation for tutorials in general, okay. Okay, so speaking of this and about tutorials, I guess this transitions to what would you, for instance, want for the next sessions, for the next talks, for these kinds of seminar? And is there a way to make it perhaps more interactive as well? Does any of you have any idea about this or any suggestion?
So one comment I have here, and others can chime in how they feel about this. Maybe like 2 talks, we had to cut down some discussions. There could not be in-depth discussions. So going forward, perhaps 1 talk, and like we don't have to take the full hour. Maybe it could be 45 minutes and 1 talk and like in-depth discussions around it. So that's one possibility.
That sounds like a good idea. Theo was also mentioning maybe creating a Slack channel for the POP seminar itself, which I think sounds great. And that's also a good way to keep track of sub-channels, if any, for different talks. I guess on a personal level, I share Asim's feeling that I saw some very, very cool stuff. And I was almost frustrated to not have a chance to discuss it more, but I'm sure there'll be some great follow-up discussions with the speakers. So I'm very happy about it.
I think a useful way to do a interactive thing would also be if people have things that they wish to formalize in F-star, but do not know how to. And if members of the community can chime in about ways to get started on that, that could also be a useful thing, either for the Slack or maybe for a in-depth discussion.
So I guess building on this idea, would there be interest, for instance, in some pair programming session of, let's say, somebody comes and says, hey, I really want to model X or Y in F-star, and somebody more proficient with F-star helps them, and there is just an interaction between the two where chat could chime in, for instance? Would that be something of interest to people?
Yes.
Okay. I guess on top of that, if we're moving to one talk per session, do you folks have any preference in terms of how long the talks should be? So even if we're planning for like a 1 hour slot, do we want to maybe limit ourselves to 20 minutes talk, let's say at most, so that we can have enough time for discussion and interactivity? Do we want once in a while to have longer talks, even though that means fewer questions? Is there any opinion on that? Thanks for taking notes, Vika.
Yeah.
Probably 30 minutes max is a good absolute maximum if you want to have discussion. But 20 minutes is probably better.
You are muted.
Sorry, yeah. I was mentioning that Cesar and Josh were advocating for shorter formats, and Alex was okay with a full-fledged lecture once in a while. Okay, that's fair.
Also, just to put it out, like not every talk has to be same format. Like, it could be the case that some seminars are 20 minutes and then 20 minutes of discussion. Some seminars are like maybe Alex's stuff takes more time, so it's longer talk. So I think, yeah, we can also just keep it flexible depending on the speaker, what they want to get out of the seminar.
Okay. Yeah, advertising the duration in advance sounds like a good idea. What about steel or low star? So I think, at least on a personal level, and for the others, please chime in as well. Low star and steel for me are just components of F-star. They are part of the ecosystem. And, I'd be very happy, at least on a personal level, to have a pair programming session on either of these things, or have a quick presentation, or attend a quick presentation. I think if there is interest, that's maybe a good thing to keep track of in terms of what exactly the topic of one talk about low star or steel would be. So yeah, if you have anything specific in mind, or if you just want a tutorial, please don't hesitate to mention it. Okay, so Nick is also mentioning in the chat that there is a mailing list for this seminar that you all should join in order to keep hearing about this and receiving all the announcements. I don't know if Nick, I assume one of you wants to also right now create a Slack channel, as was suggested by some people in the attendance.
Yeah, we'll follow up on that. Okay. I guess we're also at the end of the hour, so like maybe we should wrap up. Okay. So so please, yeah. Thanks, Aymeric. Thanks for all the everyone for the thoughts. Please do send us emails if you have more thoughts around the seminar and proposals. Yeah, please do send us what you would like to present, and format in which you would like it to be. And it's very informal, so we are happy to hear ideas and transform it that way. So I don't know, any last remarks? We should otherwise conclude. All right, thanks everyone for joining in. I really enjoyed the session. I hope we can continue it at some cadence. Thanks a lot. Bye.